Right, today we're going to look at nanoparticles and nanotechnology, and then we're going to look at fullerenes. So these are exclusively AQA kind of topics. So first of all, what are nanoparticles? Well, you need to know that the word nano means 10 to the power of -9. So you're dividing by a billion. Because milli means 1,000, micro means a millionth. So times 10 to the -3 times 10 to the -6 times 10 to the -9. Nanoscience is a study of really tiny things, essentially, in the size of 10 to the power of -9. So if you're looking at a particular nanoparticle in its pure definition, it will be a size between 1 and 100 nanometers. That is the definition. So if you want to turn 100 nanometers into meters, you would have to do 100 times 10 to the -9, which will give you 10 to the -7 meters, would be the biggest size nanoparticles, and the smallest one is 10 to the -9. So it'll be between this size. Now, scientists came up with this because they have to have a common language for tiny particles. So if you look at this, obviously you don't need to know all of these, but just as an example, nano, you put nm for nanometers. For micrometers, you put μm, which is 10 to the -6. So if we look at this diagram here, we can just look at the size of certain things. So as you can see, a carbon atom is 10 to the -10 in size. DNA, 2 nanometers, which would be 2 times 10 to the -9. Carbon nanotubes are between 5 and 10 nanometers. Then we got, each one's getting bigger, obviously. Gold nanoparticles are between 1 and 100 in diameter. Now, red blood cells are obviously bigger. They're 2 times 10 to the -6 meters. So they're micro. Then we have human hairs, and then here we have the head of a pin, which is 2 millimeters. So this just shows what equipment you can use to record it. So scanning probe microscope can be used to measure these and see them. A scanning electron microscope is used for the bigger ones. You don't need to worry about that. Okay, what you need to know is this table here. It is on your specification. Okay, so know that pollutant particles can be pollutants, pollen, or dust, and they're known as particulate matter. And we can have these particular matters. So if I just show you the spec, so you can see where this is coming from, let me show it to you now. Here we go. So as per your specification, it says nanoscience refers to structures which are between 1 and 100 nanometers in size. You need to know PM2.5, PM10, and coarse particles. So that's the bit I'm teaching you now. So PM10, you need to know, is also called dust and is the largest one, and it has this size. Okay. Fine particles are PM2.5 and are between 100 and 2,500 nanometers. And nanoparticles are the smallest, between 1 and 100 nanometers. And they don't have a particular matter value because they're so small. So coarse particles, in this case, are the biggest. Unfortunately, as I say, it looks like you should know the sizes from the syllabus, okay? I've seen this one asked in an exam in a multiple choice fashion. I haven't seen these, but be aware of it. It's on your spec. The next part to essentially talk about is this one here. As the side of a cube decreases by a factor of 10, the surface area to volume ratio increases by a factor of 10. So this is the principle that as you make something smaller, the surface area to volume ratio gets bigger. Let us have a look at some examples. If we consider a cube with length 1 centimeter, the volume would be 1 times 1 times 1, which is just 1. The surface area would follow this formula, 6x squared, where x squared is the area of the square times the number of faces, which is 6. So 1 squared is 1 times 6 is 6. So the SA over V ratio will be 6 divided by 1, giving you a ratio of 6. Now, suppose you had a bigger side cube. So if it was 10 times bigger, then maybe this is better. Yeah. So if the cube was 10, it would be 10 times 10 times 10, which is 1,000. Now the area of one square will be 10 times 10, 100, times 6 faces will be 600. So the ratio of SA to V will be 0.6 to 1. So as you can see, that is 10 times smaller ratio. So the principle is, as it gets smaller, so if you go from 100 upwards to 1, and you're making the side length smaller, the surface area to volume ratio is each time multiplying by 10. So the smaller you are, the higher surface area to volume ratio. Okay, and this gives you very special properties, because if you imagine that you're only 1 nanometer, then this ratio will become absolutely huge, because that's like 6 billion. Imagine decreasing this further. Well, this is 1 centimeter, but it's even more. You would convert it to a meter first by dividing by 100. Then you convert it to a nanometer by dividing by 1 billion. So you're going to get an absolutely massive value for the ratio. Okay. And because of this massive value, we have special uses for nanoparticles that relate to these properties. And the main one that you should know are the fact that they have a very high surface area to volume ratio, so they can be used in catalysts. They can be used in nanomedicine, so they can be fit inside a fullerene, which we'll do next, and absorbed into the body more easily. The main thing about them, the main thing is that you need less of the nanoparticle to cause the same effect. So due to the high surface area to volume ratio, a lower amount of nanoparticle is required to achieve the same effect, because it can be absorbed very readily. That's the main advantage it has. So instead of taking a pill that's 1 gram, you can take a much smaller one if it's with nanoparticles. Okay. And these are some other uses. So antibacterial properties, they can be added to polymer fibers in surgical masks and socks, and in cosmetics to improve your moisturizer by going into your skin more readily. There are, however, some dangers of nanoparticles. So although nanoparticles are useful, the effect on the body is not fully understood, because they can so readily go into your skin and into your bloodstream. So all you need to remember from all of this is that they can cause harmful side effects. Okay, so an example would be nanoparticles can be used in sun creams to protect you better from UV light, and they have better skin coverage. But it is not known whether they can go into your body and damage your cells. It is possible that when they are washed away, they might damage the environment. So in summary, you just need to know one sentence: the nanoparticles can have harmful side effects which are unknown. Now that completes nanoparticles, which leaves us with just the fullerenes to examine. So fullerenes, there it is, you see. Smaller quantities are needed to be effective for materials compared to normal particle size. And that's because of the high surface area to volume ratio. That is the key takeaway message. You need a lower quantity of the medicine if it is in nanoparticle format. Now, we've already talked about the uses, advantages and disadvantages. They might give you appropriate information in a table and ask you to evaluate, reach a conclusion, which one is better. Okay, so that is an area to be aware of. Now we're going to look at fullerenes. Now, we've already done graphene before, when we did diamond. So now we're just going to focus on the fullerene aspect, which is this. Okay, so fullerenes are molecules of carbon atoms with a hollow shape. They have usually hexagonal rings of carbons, but they can contain 5 or 7 carbon atoms. And the first fullerene, which we actually already talked about, is the Buckminster fullerene, C60, and that's the football shape. Now, you should be able to recognize fullerenes and graphenes from diagrams and give examples of fullerenes, such as carbon nanotubes. So if we look at the notes on this, we're going to use this. It's a very kind of small part of the spec. So fullerenes have a hollow tube or sphere shape, so you can fit nanoparticle medicine inside to deliver it in a particular body, a particular part of the body. They have also a very high surface area, and they can trap catalysts inside them. They can also be excellent lubricants because they have this spherical shape, so they can roll. And the first fullerene was called the buckyball with C60, 60 carbon atoms, and it's got 20 hexagons and 12 pentagons in it. Now, we did talk about it before, but again, I can mention the Buckminster fullerene is a simple molecular structure, but it has a much higher melting point than other simple molecular structures because it is so much bigger than other molecules, which means increased intermolecular force of attraction. Each carbon bonds to 3 others, so there is 1 delocalized electron per carbon atom. However, it cannot conduct electricity because the electron cannot jump from one Bohr molecule to the next one. So it's a rare example of having delocalized electrons and not conducting. Right, the last one is just nanotubes. So fullerenes can also form cylindrical shapes in these nanotubes if they're rolled. They have a very high tensile strength and they're resistant to breaking or stretching. Just like in graphene, they conduct electricity very well because they do have 3 bonds only, so 1 delocalized electron, and this time it can move throughout the structure. So they can be used in electronics and nanotechnology. And that's literally all you need to know. There's no need to really make a big fuss of this part of the specification. It is not so in depth as you can see here. Carbon nanotubes are cylindrical fullerenes with a high tensile strength, a high length to diameter ratio, and they're good for these 3 things. This is literally rote learning. There's not much more else you need to know about it. Okay, but having said that, when it comes to the nanotubes, nanotechnology, and this part, you can be asked to do some calculations. So I'm just going to give you an example of that to finish off. I'm going to give you an example. So bear with me. We're going to use this question here as the example. So a silver nanoparticle can be a cube with a side edge length of 60. Calculate the surface area to volume ratio. Give you answers in meters squared and in meters cubed for the volume. So what's important is that you don't use the 60. You convert it to meters. So it becomes 60 divided by a billion, essentially. So 60 times 10 to the minus 9. So to find the surface area, you do 6x squared, which means you square this and times it by the 6 faces, and you get this. Make sure you put in brackets on your calculator and practice doing this. Easy to get it wrong, even though it looks easy, it's very easy to make a mistake. For the volume, you just times each length by itself 3 times. So it's x cubed. So 60 times 10 to the minus 9 cubed, and you get this. Now, when you divide these 2 numbers, you do this one divided by this one, and you'll get 100 million to 1 as the ratio, which is quite significant. It shows you the high surface area achieved. Explain why some people are concerned about the use of silver nanoparticles. Well, because they can be harmful to the health. There's unknown side effects that are harmful. Just make sure you put the word harmful in there. Okay, that completes the lesson on fullerenes and nanoparticles. So that will then complete your bonding topic. So well done, and just practice through all the bonding questions, making sure you're good with the keywords.